Is Chemistry 302, lecture number 9, an introduction to simple equilibria involving the solubility of salt in water. So the first thing that we're going to take a look at in terms of this exploration of how you apply the Rice expression in chemical equilibria to chemical reactions is going to be looking at the chemistry of dumping salts into water. We choose this one here because it turns out that mathematically, on a certain level, it is the simplest that I can show you. Let's take something like some sodium chloride. I want to dump some sodium chloride into water, and when I do, I make sodium ions and I make chloride ions. This is the dissociation of a salt. We've actually explored this in a variety of ways throughout the year, and I'll come back and refresh your memory about some of this. But I show this to you here right now because I can now put it in the context of a Rice expression and the equilibrium constants associated, or the equilibrium calculations associated with it. So there's my reaction. I can talk about my initial amounts of sodium chloride, the change in the equilibrium, and when it's all said and done, my K for this reaction is going to be equal to my sodium ion over my chloride ion divided by sodium chloride, except for you immediately say, wait a second. Salts are solids. Solids have an activity of 1. I can immediately do these problems without a denominator. Isn't that great? You can see why we choose to do these problems first. Mathematically, they're incredibly simple because I don't have to mess with that term in the denominator. As a result, it's just these two numbers multiplied together in simple salts that I have to worry about. There is a special name that we give to the equilibrium constants associated with these kind of solubilities of salts in water. It's called a KSP. So this is the K solubility product. You see, it's the solubility, the concentration of each of these in water. Their product is equal to the equilibrium constant. And so we're going to learn in today's lecture for some simple examples how it is that we work this kind of problem. And we do that understanding that we don't have a denominator, so it's simply going to be the product of a couple of numbers that's going to give us our result. Now, before we take a look at the quantitative aspects of solubility product chemistry, so that we can learn to use these KSPs to tell us things about our salt solutions, it's important to look at what we've learned to this point throughout chemistry. And the very first thing we learned about dissolving salt in water is whether or not they dissolved or not. There was a point back in high school chemistry where you learned the solubility rules for salts. The solubility rules for salt, there were a whole bunch of them. I had to learn these large trees when I was your age, but you don't have to learn them now because we don't believe you should have to learn stuff. But what I learned were things like this. The carbonate ion, sulfide ions, hydroxide ions, phosphate ions did not tend to dissolve when thrown as salts into water. So if I had a compound that was like calcium and I combined it with carbonate, calcium carbonate, it wasn't going to dissolve in water. Calcium phosphate, it wasn't going to dissolve in water. In fact, that's what made stuff rocks. On the other hand, I learned solubility rules like this, that the alkali metal ions like potassium ion and sodium ion, nitrate ion, for example, ammonium ion, these always did dissolve in water. So I had these two categories, the stuff that dissolved in water, the stuff that didn't dissolve in water. So I could use those to predict different kinds of chemistry. I could take some lead nitrate, for example, and dump it into water and say, does lead nitrate dissolve in water? Well, yeah, it does, because nitrate ions dissolve in water. So there's my lead nitrate floating around. And what about potassium chromate? Well, because potassium ions dissolve in water, I've got some potassium ions and some chromate ions dissolving around in water. And then I ask this question, what happens if I mix these two things together? Well, because nitrate ions like to stay in water, and because potassium ions like to stay in water, they don't do anything but remain soluble in water. But lead ion and the chromate ion turn out to not want to stay in solution. So they fall to the bottom as a precipitate. So this is a reaction in which I was able to predict from my solubility rules what would dissolve and what would not dissolve in water. As I said, this is something you learned back in high school. I don't expect you to have all that much of this memorized. In fact, I have a general set of rules I'll show you in just a second that makes it easier to follow what's going on. But the solubility rules were our first pass at understanding what happened when you dumped salts in water and predicted whether or not stuff would stay soluble or whether it would become a precipitate.